Welcome to PH 4105, Advanced Mathematical Physics, in which we are currently treating differential geometry. This is lecture number 13. In the previous lecture, we had met a very important player, especially in mathematical physics, the vector field. And we have seen that the vector field comes in two avatars. In its first avatar, a vector field X is simply a map from the manifold M to its tangent bundle Tm, but a special kind of map. The restriction is, it maps a point P of the manifold to a vector xp which belongs to Tpm, that is, a vector which is stuck to the point P of the manifold. In its second avatar, X can also be thought of as a map from C infinity M, the set of all smooth functions on the manifold M, to phi m, r, which is just the collection of functions from M to R. That is, you can also think of X as something which changes a function into another function. And the function xf, which you get when X, the vector field, acts on the function f, is defined in the following manner. The value of the function xf at the point P is defined to be the action, or rather the result of the action, of the vector xp, which is the value of the vector field at the point P, eating up the function f. And of course, since xp, a vector at a point, is actually a linear functional, it will eat a function and return a number. So xf, acting on a point on the manifold, returns a number, which is exactly what we mean by a function on the manifold, or rather a real valued function on the manifold. Now it turns out that these two avatars are equivalent, despite the fact that X looks very different in these two guises. You can show that knowledge of one avatar completely tells you what the other avatar will be doing, which is sort of obvious, at least in this definition. Given avatar 1, it's very easy to figure out what avatar 2 will do. The converse takes some work, but we have already shown that in the last lecture, that if you are given a map from C infinity M to phi mr which satisfies certain properties, you are going to get a well-defined vector field, in the sense that you will get for every point P on M, or maybe a subset of M, a vector tied to that particular point. We will be dealing mostly with smooth vector fields, where X belongs to this set called fracture X of M, or curly X of M, may be an easier way to put it. And the feature of smooth vector fields is that when they act on smooth functions, the resulting function is also smooth. So this X, which belongs to this fracture X M, is a map from C infinity M to C infinity M. Now the particular properties which vector fields must obey in their second avatar, in order to be really leading to a vector field in avatar 1, are the following. Acting on a linear combination of two functions, af plus bg, where f and g are functions and a and b are just real numbers, x returns the function which is given by a times xf plus b times xg. And x acting on a product of two functions fg is f, the function f, times xg, so a product of two functions, plus the function g times the function xf. Now, for obvious reasons, this is called the derivative property, and hints at the fact that the vector field can also be thought of as a differential operator. An operator because it changes a function to a function, differential because it behaves on a product just the way a differential would. Now we can also talk about combining vector fields, and we do it by the following manner, either using avatar 1, which is here on the left, ax plus by, this combined vector field where a and b are numbers and x and y are vector fields, returns at a point P of the manifold the vector given by axp plus b yp. Now, In avatar 2, this statement simply translates to ax plus by acting on a function f gives you a times x acting on f plus b times y acting on f. Another property which has to be thought about is how do you multiply a vector field by a function on the manifold. Not just a real number but a function this time. And by definition, fx acting on p, again this is a definition, is f of p times the vector xp. And the equivalent version in the avatar 2 statement is simply fx acting on a function g gives you the function f times x acting on g. Now, we had also seen that you could use coordinate basis vector fields del xi, whose values at each point p. Del xi at a point p is simply the ith coordinate basis vector to TPM at that point p. So basically the tangent to the ith coordinate curve passing through the point p. And in terms of these vectors del xi, these vector fields, can write any arbitrary vector field within the domain of this particular coordinate set in the following form. Capital Xi times del xi, of course summed over I, that's implied in all of this, where capital Xi is a function which you can easily get by applying the vector field a capital X on the function xi. So, these are nothing but functions you get by applying the vector field on the coordinate functions themselves. And this leads directly to a notion which is very familiar to all physicists. At least all physicists have studied slightly advanced mathematical physics. If you do a change of coordinates from one chart where the coordinate functions are small xi to another chart where the coordinate functions are small x prime I, the coordinates transform in the following manner. Capital X prime I, the components here, are nothing but del x prime I, del xj times xj. This is a mistake. This should be j. Of course, summed over all j. Now, today we are going to carry on from this point. In fact, we will start with a specific example of a coordinate transformation which should help to clarify the concept here. For this example, we will consider a very simple manifold. Here M, the manifold, is simply R2, the set of all pairs of real numbers, or geometrically a plane. Here we will consider two charts. The first one is a very familiar one, u, phi, where u is the entire manifold M and phi is simply the identity map. This means, of course, that to each point P on the manifold, you assign two numbers x and y, which are nothing but our familiar Cartesian coordinates. Now, given that we are using Cartesian coordinates here, the other chart we are going to talk about, there are no prizes for guessing what that one is. That's simply v, chi, where v, the domain of the chart, is given by the entire plane from which the origin has been taken out. Not just the origin, actually all points along the negative x-axis have been taken out. So y equal to 0, x less than equal to 0. The origin and the negative x-axis has been taken out from the plane, and you use chi, which is something which simply maps a point P to the polar coordinates r, theta. And we already know the relationship which relates r theta directly to xy, that is coordinate functions of chi to coordinate functions of phi. In fact, this is actually the transition function phi composite chi inverse. And here we all know this familiar formula: x is r cos theta and y is r sin theta. Note that the domain of the polar coordinates is not the entire plane. The origin, of course, has to be taken out, because at the origin where r is 0, theta can take any value. So if you allow the origin to be a point within the domain of this particular polar coordinate chart, you would not have one-to-one mapping between points on the manifold and your coordinates. The origin would have infinitely many different values for coordinates. So that point is out. You have to actually take out not only the origin but an entire line joining the origin all the way to infinity, simply to ensure that you do not have two very nearby points ending up with vastly different values for theta. That is, in order to prevent the jump that you get when you go all the way around the origin from theta to theta plus 2 pi. If you want to get a single valued continuous function, you have to take away a line joining the origin to a point at infinity. Here we have just decided to go with a simple choice where we have taken away the origin and the entire negative x-axis. Now, because of this precise choice, the other transition function, chi composite phi inverse, has a slightly more complicated form than what we are used to. We are used to seeing the inverse of this transformation in the form r equal to square root of x square plus y square and theta equals tan inverse y by x. But you must realize that that transformation actually works well as long as you stay away from the y-axis. On the y-axis itself, tan inverse y by x goes to a singularity and jumps from pi by 2 to minus pi by 2. Not a very nice thing to use. Instead, what we will use is the following. R is square root of x square plus y square, and theta for a point P will be defined by this. X dy minus y dx by x square plus y square integrated along a curve where the curve C is any curve which joins 1, 0 to the point P. I will just let you figure out exactly why this means the same thing as the kind of angle we have been talking about. Note that in our plane, this entire negative x-axis and the origin are out. They are not part of the plane. So let me just use red to show that they're out. And here, for any point P on the manifold, what you do is join 1, 0 by some curve and integrate x dy minus y dx by x square plus y square along that curve. You should realize that if for any small piece of the curve, this integrand here, x dy minus y dx by x square plus y square is exactly what we call d theta. And when you integrate it along any curve joining P to 1, 0, you will get the angle, and you will get the angle in a smooth manner so that for every point here or here, you will get an angle independent of which curve you actually choose. Whichever curve you choose, you get the same value. Now, the fact that whichever curve you choose, you get the same value might tell you that x dy minus y dx by x square plus y square is an exact differential. However, there is a catch there. Indeed, if we were to check whether this differential is exact or not using the trick that you had learned in the first year, where m dx plus n dy is said to be exact if it obeys the following: del m del y equals del n del x, you will actually find that x dy minus y dx by x square plus y square satisfies this particular criterion. However, if you allow the entire plane to be your domain, of course taking away the origin, then despite satisfying this particular condition, m dx plus n dy, in this case this differential, would not be an exact differential. The easiest way to see that it's not an exact differential is consider any closed curve, maybe a curve which starts at 1, 0 and goes all the way to 1, 0 by going around the origin. It's not going through the origin. So, if our domain had just left the origin out, but had left the entire negative x-axis in, we could have such a curve. But if we use such a curve, the integral would simply become 2 pi and not 0. And that's a sure shot sign that the integrand you are integrating is not exact. We will have a lot more to say about exact differential forms and closed differential forms, which this is an example of. It's something which satisfies this. And the connection between closedness and exactness when we talk about differential forms later. For the time being, all I want you to realize is that once you have taken the entire negative x-axis out of your domain, the curves cannot go all the way around the origin, except maybe here. And if you actually had a curve which goes like this, which of course does not go around the origin, such a curve would actually give an integral of 0 for the entire curve. So, in this domain, x dy minus y dx by x square plus y square actually behaves like an exact differential. And so, whichever curve you take, you do get the same integral, and this theta becomes a perfectly well-defined quantity for a point P. To summarize, theta equal to tan inverse y by x is not really well defined at x equal to 0. That's one big problem. Here we don't really worry about that. This theta is really the angle taken from the x-axis counterclockwise. If you do that, you are actually going to get this value. But you're not allowed to have any point on this entire negative x-axis, which means when you're right here, you're going to get something close to plus pi. When you're right here, you're going to get something close to minus pi. But you're never going to get a jump from pi to minus pi because you're not allowed to go across that line. With this rather lengthy discussion on the connection between Cartesian and polar coordinates, let me move on to the actual problem. By the way, this problem has been taken from the same textbook that I had alluded to earlier, the book by Torres del Castillo. And many of the problems we will work out during this sort of lectures will actually be from that source. Not necessarily all of them, but some of them definitely. Now, the problem essentially goes this way. It talks about a vector field x whose components in the basis provided by small x and small y, the original basis, so to speak, are 2xy and 1 minus x square plus y square respectively. That is, capital X is given by this 2xy times del del x plus 1 minus x square plus y square del del y. Let me remind you that del del x and del del y are vector fields. They are not partial derivatives really. They are vector fields whose values at a point P is del del xp and del del yp respectively. And these vectors, del del xp and del del yp, are tangent vectors to the coordinate curves corresponding to the coordinate functions x and y passing to the point P. Here, of course, the geometric meaning of this is very obvious. If this point P has x and y as coordinates, the coordinate curve for x passing to the point P is simply one in which x and x alone changes, the rest don't. In this case, the rest means y doesn't. So this is my coordinate curve. Of course, it's supposed to be exactly horizontal. Excuse my drawing there. And y would be this coordinate curve, a vertical line going through this. And del del x and del del y would be essentially unit vectors, or rather vectors, which you get when you move through a unit distance or a unit parameter value along the x coordinate and the y coordinate curve respectively. And these are nothing but our familiar I and j. Physicists, at least in non-differential geometry scenarios, would usually represent these vector fields by 2xyi plus 1 minus x square plus y squared j. Now what we want to do is ask what are the components in the del del r and del del theta basis. Now let me at least provide a geometrical meaning to these vectors here. Del del r and del del theta again are not really vectors but vector fields. At a particular point P, del del r and del del theta will give you basically what the functions change like when you move along coordinate curves. Now, the r coordinate curve is one in which r and r alone changes, theta does not, so it's basically a curve, actually a straight line which goes to the origin straight out. Okay, pardon my rather nasty drawing, it should really be a straight line. And del theta would be one in which theta and theta alone increases, keeping r fixed. So basically arc of a circle. So this is the r curve, this is the theta curve. And if you change r by a slight amount, ask how fast is the function changing along this line, you actually get the del r. That's the result of del r acting on the function. The result of del theta acting on the function is when you change theta by a small amount and ask for the rate of change of f as you move along the circular arc. So del r essentially is very easily identified as our radial vector r hat, which we often use in initial physics courses, and del theta similarly should be akin to theta hat, but there is an important point to worry about here. Del r actually is r hat, but del theta is not theta hat, it's related to theta hat. Theta hat, remember, is a unit vector, a vector whose length is 1. Now here we are not really talking about lengths as of now because we have not introduced the notion of length on a manifold. But by borrowing the standard notion of length that we already have from ordinary geometry, it's easy to figure out that del theta would not really be a unit vector. Rather, 1 by r del theta would be a unit vector. It's easy to see why. When you change theta to theta plus delta theta, the point doesn't really move to a distance of delta theta, it moves to a distance of r times delta theta. To compensate for that extra factor of r, the unit vector actually is 1 by r del theta. We have actually talked about these things earlier. I'm just repeating them here in case you have forgotten. Just to point out that this is really not 1 by r del theta once again. It's actually 1 by r del theta at a point P. With this background, let us start solving our problem. We want to express the vector field x in the del r and del theta basis. And for that we need the component functions. The component functions, of course, are nothing but the vector field x acting on the coordinate function r and on the coordinate function theta respectively. So let us first figure out what x acting on r is. X acting on r, of course, is given by this operator, or this vector field really, acting directly on r, and that gives us twice xy del r del x plus 1 minus x square plus y square del r del y. Note that del r del x and del r del y are actually, strictly speaking, the partial derivatives with respect to the first and the second component function for the chart u, phi of the proxy function corresponding to r. But when you write something like r equals square root of x square plus y square, you are actually directly talking about the proxy functions. So, as far as this calculation is concerned, del r del x and del r del y can be evaluated just like ordinary partial derivatives. And using the fact that r is square root of x square plus y square, it's pretty easy to figure out that this partial derivative is essentially x by square root of x square plus y square, and this one is y divided by square root of x square plus y square. Combining them together gives us 1 plus x square plus y square into y by square root of x square plus y square. This is simple algebra of combining this with this and taking the y common. And now we want to express this result in terms of the polar coordinates r and theta. And that's pretty straightforward. Y divided by square root of x square plus y square is nothing but sine theta. And 1 plus x square plus y square is of course 1 plus r square. So this is what xr is. Okay, granted that we have managed to figure out what x will look like in polar coordinates. The component functions here are simply given by this and this. But couldn't we have figured this out using first year, say, physics honors methods as well? Standard first year mathematical physics course. The answer is we could very well have done that. For that, what we would need is, in the first year, we would have written the same vector field x in the form twice xy I hat plus 1 minus x square plus y square j hat, where I hat and j hat are, of course, the Cartesian coordinate unit vectors. And what we really want to do is rewrite these in terms of r hat and theta hat, the radial and cross-radial unit vectors. Remember, these two unit vectors actually make an angle of theta with the I direction. In fact, r makes an angle theta with I. Theta hat makes an angle theta with j. And this is why r hat and theta hat actually depends on exactly which point on the plane we are talking about. On the other hand, I and j are basically the same vectors throughout. So, firstly, we need to be able to rewrite these coordinates x, y and this component here all in terms of polar coordinates. That would be pretty straightforward. We would also need to be able to change the I and the j into the corresponding polar vector equivalence. Now, from this picture, it's pretty easy to see that the component of I in the direction of r is simply cosine theta. Remember, I and j are both unit vectors, so are r hat and theta hat. And the component in the direction of theta hat would be sine theta, but it's in the direction of minus theta hat, so minus sine theta hat. J, on the other hand, has positive components in both the radial and the cross-radial direction, and the components are sine theta for r hat and cosine theta for theta hat respectively. So, what we need to do is simply replace these components here by the polar coordinate equivalent, as well as replace I and j by cos theta r hat minus sin theta theta hat and sin theta r hat plus cos theta theta hat respectively. Once we do that, collect all the terms with r hat together, that is this with this and this whole bracket with this together here, and all the terms with theta hat together again. Cancel out a few factors, would combine them together. You will ultimately very simply land up with this expression. Pretty straightforward calculation, nothing really very different from the ones we have done previously. Of course, in this particular form, our vector field looks slightly different. At least the components look slightly different from the components that we had figured out earlier. But that's simply because our del theta component, the theta component, x theta, came out to be 1 minus r square over r cosine theta. And here the cross-radial component is given by simply 1 minus r square cosine theta. But that difference is easily explained away by what we had said earlier. Theta hat is a unit vector. Del theta is simply a tangent vector which measures how fast a function changes when you move in the curve where only theta changes. And there is a factor of 1 over r between the two. So if you plug in the factor of 1 over r, remember that this theta hat is really 1 over r del theta, and this r hat is directly del r. We will see that our more elementary calculation based on first year mathematical physics actually matches exactly the result that we had obtained earlier. Our basic aim was to show that you could actually work this out directly by applying x, the vector field, on the coordinate functions, or you could of course use your first year mathematical physics method. In this particular problem, which was a pretty simple one, both methods are equally convenient. However, it's often the case that the elementary method would be very, very difficult to use, and you would really be much, much better off using the more advanced methods which differential geometry teaches us. Now, if you have been trained in the standard physicist index gymnastics methods for carrying out transformation of coordinates, you may have already realized that what we actually did when we applied the vector field x on the coordinate functions r and theta was really apply the standard coordinate transformations, but maybe a bit more directly. In the last lecture, we had actually proven that applying the vector field x directly on a new coordinate system, x prime I functions, would directly give you the standard transformation rule between coordinates that physicists are used to. Just to make that connection very clear, let me remind you that the way a physicist would usually approach the problem is the following. In calculating the first coordinate in the new frame, x prime 1, which is nothing but xr, she would actually use this rule, del x prime 1 del xj, capital Xj. The capital Xj is a jth component in the old coordinate system. Expanding out this summation, in this case j can only take two values, 1 and 2, this reads del x prime 1 del x1, capital X1, plus del x prime 1 del x2, capital X2. Since x1 and x2 are nothing but our old friends x and y, and x prime 1 is r, this obviously translates to del r del x times x1, which is capital X acting on x, the x component, plus del r del y times capital X acting on y, the y component. Putting all this together, we end up with this expression, which is exactly what we had obtained when we had applied the differential operator or the vector field capital X directly on R. I'm not going to repeat the calculation for you, but it should be obvious that both x prime 1 and x prime 2 can be calculated in this manner, and it would definitely coincide with what we had calculated by directly applying capital X on R and theta respectively. I hope that the example that I've worked out today has completely convinced you about how to go about transforming components when you change your coordinate system. In the next lecture, we are going to address the question, can we push a vector field forward the way in which we have managed to push vectors forward from one manifold to another? Is it always possible? Is there a catch somewhere? Etc., etc. But let's wait till the next lecture for that. Bye for now.